Hello, today I'll be explaining recurrent neural networks. I am Tiffany Williams, and we will be looking at how they work, real world examples, and the main challenges when training them. So let's jump right in. So, what's a recurrent neural networks? Recurrent neural networks are built to understand sequences and how the data unfolds over time. Um, The network carries information from one step to the next using a hidden state, and this enables them to recognize patterns over time, such as predicting the next word in a sentence or the next day's temperature. Some of the ways that you may recognize using recurrent neural networks is recommendations or speech recognition. So, for example, when you're sending a text message, you may notice that you start typing a couple of words and then a line of words are suggested for you. That's because the model is looking at what you previously typed or input, and it is suggesting things based on what they predict you will say next. It sometimes uses sentences prior, or it may just use a few words prior to kind of redirect what you're saying or help you with the next word in the sentence. It also helps you with correcting spelling errors or even converting spoken words to text. So, when you're using a language translation, yes, again, that is a recurrent neural network that is taking in information and spitting it back out based on the context that it previously gathered. You may have guessed it by now, but Siri and Alexa rely on recurrent neural networks and their advanced versions to understand natural language and tone over time. So, although you may not be familiar with the term recurrent neural network, you probably have encountered or utilized some of the applications that use these models on your phone, on your tablets, on your computers, multiple places that you have probably utilized this neural network. So you can think of a recurrent neural network like your short-term memory, where it retains sequences of information to quickly recall and process. It's sort of like remembering information during a conversation. You remember what was said before, so you can respond appropriately based on what you previously heard. That's essentially what recurrent neural network does. It keeps track of prior context so it can make smarter predictions. Sequential actions, they help learn a complex task by breaking them into manageable steps. That's what the network does. It pays attention to what happened previously and learns what's happening and continues to take it throughout the model or the network and store that and retrieve it at the appropriate time. Some of the popular recurrent network libraries or frameworks used to build and train the networks include TensorFlow, Keras, and PyTorch. These libraries simplify model creation and visualization, helping data scientists focus on design and interpretation rather than code complexity. So, I definitely will be utilizing some of these libraries going forward because work smarter, not harder, right? So let's get into the architecture and understanding the actual sequence flow or how the data is processed and maintains the state over time. And one of the things that makes recurrent neural networks so powerful is a recurrent loop that it captures context over time. But let's just see how this works. So, at a high level, each recurrent neural network step takes an input. And if we can see over to our left, far left, figure A, starting at the bottom, one hot encoded word, that's the input layer. And then it takes the input and the previous hidden state and combines them and produce an updated hidden state. So that would be the H sub T. That's going to be the hidden state. And that hidden state represent what was learned from the sequence. And so that predicted word likelihood is the output. Some things to note about recurrent neural networks is for each timestamp, there is an input and an output. And a timestamp is basically the specific position within the sequence. So if we look at figure B, timestamps are vertical. So our first timestamp would be x1, h sub 1, y sub 1, and those weights that's associated with each of those input layers and the target word or output layer. That is a sequence here. This is a timestamp. And one thing to note is the weights of each timestamp is associated only with that particular timestamp. It does not carry to the next timestamp or the next layer, sorry. It updates based on what it learns. So it combines to create an updated hidden state or weight. Some of the common activations used in recurrent networks are hyperbolic tangents or tanh and sigmoid. And the function y sub t here is used to learn the output values from those hidden states. But I'll show you just how. I know that was a lot to take in at once. So I'll show you just what I mean, a real world example. So here we have, you remember I mentioned one hot encoder. So the one hot encoder is used for the input vector, as you can see, with zeros and ones associated with the word choice. We have the possible word choices that may come up next. And we have that hidden state with the weights as well. So again, we have the vector is 1000 in our first timestamp. As I mentioned, the weights are shared across the timestamp vertically, but not across the layers. The layers, the weights are updated here, whereas vertically, they are shared throughout the timestamp. But for the next layer, there is an updated weight that goes along with it. And the values within y sub t here at the top, which is the output, those values are not probabilities just yet. Those are likelihood of presence. So the likelihood that the would be the next word after the is negative 1.2. The likelihood that cat is next is 1.3. The likelihood that chase comes after the is negative 0.8. And the likelihood that mouse comes next is 1.7. And the higher the likelihood, the higher the value is the higher the likelihood. So the actual target word is cat. And as we can see, mouse was actually higher than cat, but that's because both of them could be used in the sentence. And as the model continues in more iterations, it continues to kind of learn the context of where you're taking the sentence or what you're talking about. So the input was the, we predicted it would be mouse, but it actually ended up being cat. So that is the output for the first timestamp layer 1. Now we go to input that. As you can see, the vector now changes from 100 to 011 for cat. The weight was updated in the hidden state. And now we look at the likelihoods of presence for the cat. The is negative 0.4. Cat is negative 1.7 because sure wouldn't want the cat. The cat chased is 1.9 and the cat mouse is negative 1.6. So we would choose chase, which is correct. That's what the target word was. So now we start a new layer, the cat chase. Chase is a new input layer. The vector changed. I think you get it now. As you can see, it got way more accurate in the predictions going forward because more iterations happen. As we said, these are not probabilities just yet. These are likelihoods. But softmax will actually take those continuous values and use the negative log of the correct words at each timestamp and aggregate those into the loss function, and that's where we will get our probabilities at the end. So let's talk about training the recurrent neural network. We use something called backpropagation through time. So when training a recurrent network, backpropagation through time basically works by unrolling the network across each timestamp so that the model sees how predictions evolve over time. Then the algorithm backpropagates the total error through all of these steps and adjusts the weight. So the challenge with this is there's maybe a possible memory usage, and it can be computationally heavy, like for long sequences, and that can lead to issues like vanishing or exploding gradients. And this can be where the model forgets earlier information or even becomes unstable. So this is where we get truncated backpropagation, and that limits how far back the new network backpropagates the error. So it shortens how far it goes back. So for instance, it may go back only 5 or 10 steps instead of going back the entire sequence. And this makes training faster and more stable while still allowing the model to capture meaningful short-term relationships. So I mentioned some gradient challenges such as vanishing gradients and exploding gradients. So a vanishing gradient occurs when weights become too small during backpropagation, leading to minimal updates, and it hinders the learning in deep networks and making it hard to capture long-term dependencies. Contrarily, exploding gradients is the opposite. It's excessively large, the weights kind of implode, and it causes numerical instability. And this can cause the training process to diverge and be challenging and unpredictable. So there are some techniques that we can use to mitigate this. One being GRU, that's gated recurrent unit, or LSTM, which is long short-term memory cells. Those are both designed to help with vanishing gradient problems. So, long short term memory cells, they introduce gates that control what information is kept, forgotten, or even output to each step. This allows the model to maintain relevant context for longer periods. Now, the gated recurrent units are streamlined versions of the LSTM cells. They simplify the structure by combining the things that were forgotten and the input gates into a single updated gate. This makes it faster to train while still effective at managing long term dependencies. So, let's do a quick recap of what we have covered today. Recurrent neural networks are built to understand sequences. They remember what came before and allow the model to recognize patterns that depend on context. Some of the uses of recurrent neural networks is forecasting, text prediction, speech recognition, um, and it can sometimes lead to challenges such as vanishing gradients and computational costs. But we have long short-term memory cells and gated recurrent unit models that improve those limitations and allow recurrent neural networks to retain long-term context more effectively. So I hope you have a better understanding now of recurrent neural networks. Here are my references if you would like to learn a little more. I hope you have enjoyed and have a great day.